Okay, if you just bear with me for 1 second while I set up the slideshow so that we can begin for my point. All right, so today we have Water and Solutions, Chapter 10. And so, first starting out with what are the properties of water? Major constituent of living things. So, that just means that water is what most things are made of. In humans, we are 60 to 70% water. We then have that water is the universal solvent, meaning it dissolves most liquids or most molecules, excuse me. So you've noticed that most times when you are dissolving anything at home, you dissolve it in water. And then water has a solid phase that is less dense than the liquid, meaning ice. Yes, so ice is less dense, and we know that water floats. Ice floats. You have to forgive me. All right. One of the other things that we may not know about water is that it has a high specific heat. What this means is that it has heat retention. It actually can retain heat. And so this is great for climate stabilization. So this is why sometimes you can live in an area like California where it's near the water and always be cooler. It has a high latent heat of vaporization. This means that it has a cooling effect, and we see this when we sweat. If you're at the gym working out hard, you go the sweating and it automatically cools you off, and that's because the high heat, latent heat of vaporization. And then we'll find out that all of this is caused by the chemical structure of water, which we will take a look at next. So, looking at water, water has a bent configuration, and as you see, I tried to show you the bent configuration, which is just following these blue lines. We also call it a lattice. So, one of the great things about water, to remember about water, although it is a great thing, is that it's a polar molecule. Why is it polar? Because it has polar covalent bonding. So please, please, please remember that term, polar covalent bonding. Okay? From last week, you should remember the term covalent, which means sharing of electrons. And then you should remember ionic was transferring of electrons. And then you had hydrogen bonds, which were weak bonds, but they were plentiful. Like they were seen everywhere. So not only does water have polar covalent bonds, and polar means that you have an element that is more electronegative than the other elements present. And for this instance, it's oxygen is more electronegative than hydrogen. And so because of that, it creates a polar molecule. Water also have hydrogen bonds, and it has hydrogen bonds. And if you remember again, hydrogen bonds are the weak bonds. And I show you here that you can have one hydrogen of one molecule bind to the oxygen of the other molecule, water molecule, and this creates a hydrogen bonds between both of them. And because these bonds are weak, they can break and reform, and this is why you can see water traveling across your car, and you'll see, I call it the bead game, beads of water, and which water can reach the end of the car first. Yes, I've been bored before while traveling. And so if you see that, you see that the water will stick together. And it's because those hydrogen bonds are reaching out to the next water molecule saying, join me. And this is what happens. All right. So key here to remember that water is a polar covalent bond, and hydrogen bond. All right. So using water gives us solutions. And so a solution is a homogeneous mixture with uniform composition throughout. So remember, I think last week we talked about homogeneous, heterogeneous. Homo meaning same, hetero different. So water gives us a homogeneous mixture throughout. So it is always, when you're using a solution, composed of a solute and a solvent. And so you may have never heard those terms before, but you use them all the time. So a solute is the substance being dissolved, and the solvent is the substance doing the dissolving. And so the solute, if we were making Kool-Aid, we'd have Kool-Aid itself, sugar, and water. And so what we will have for the solute is our Kool-Aid and sugar. And then what we have for the solvent would be our water, is what is doing the dissolving. So these are two key terms to remember: what is a solute and what is a solvent. So if you look here at this picture, can you tell me what is the solute and solvent? Yes, So the salt crystals that you see going in right here will be considered the solute because it's what's dissolving. And then, hey, all of this that you see here, the liquid, which we'll say is water, it's the solvent. It is what is doing the dissolving. So when you have a mixture, we have to talk about solubility. And this is how readily or completely a solute dissolves in a solvent. And so when this happens, you have a soluble ionic compound dissociate into ions when it dissolves in water. Insoluble, mostly undissociated, and therefore it'll form a crystalline structure. What does this mean? All it means is that when something is readily available to dissolve in water, it will dissociate completely. That's why we call it soluble or solubility. So things that dissolve completely mean that it's soluble. And so the key term to remember here when we talk about solubility is like dissolves like. Now you may have or may not have heard, you may have heard opposite attract, where in this case like dissolves like. That means that if you have a polar covalent solvent or liquid, it will dissolve polar covalent solutes. Look at there. So polar solvents dissolve polar solutes, and the same for nonpolar. And if you remember or have no clue what a nonpolar solvent would be, nonpolar would be like fats. So nonpolar covalent solvents dissolve nonpolar covalent solutes. So now we can say like dissolves like. Polar dissolves polar, and nonpolar dissolves nonpolar. And this is all your chart is saying here, that if I have a solute ionic, we'll just not look at because that will just mess us up. But if I have a polar solute, meaning some type of polar crystal structure like that I'm using, that it will be soluble or able to dissolve in polar solvent or liquid, but it will not be able to dissolve in a nonpolar liquid or insoluble. For nonpolar, the solvent, if it's polar, nonpolar will not dissolve in it, but if it's nonpolar, it will dissolve in it. So again, like dissolves like. Polar dissolves in polar, and nonpolar dissolves in nonpolar. So just keep those things in mind. Polar dissolves polar, nonpolar dissolves nonpolar. So on the test, you'll get it in the form of, I have a polar solution. What solute would dissolve? And it'll say a polar solute, a lipid solute, magnesium, zinc. And you'll say, well, hey, if I go by the term like dissolves like, and she has a polar solvent, then she has a polar solute. Okay? That's how that works. All right, so now that we're talking about water and we're talking about solubility, we have to talk about concentration. And anytime I think about concentration, I think about the washing liquid that they use as detergent that we use. And it always says, oh, you can do 40 loads because it's 10 times more concentrated. I never believe them, so I always use 2 cups instead of 1. But concentration just talks about the relative amount of solute to solvent. And that just means that you always have more solute inside that liquid. So it's supposed to be stronger. Another more, I think, palatable example is Kool-Aid. You have concentrated and dilute Kool-Aid. What makes it concentrate? The more sugar you use. The more sugar you use, the more sweet it is. The more we call it ghetto Kool-Aid versus dilute, where we call it watered down Kool-Aid, or just colored water, as my grandma would say. So when we think about things being concentrated and dilute, concentrated means you have a large amount of the solute. Dilute means you have less amount of the solute. So we want to talk about this equation right here on concentration, because I know that sometimes throws people off and we're not at physics yet. But what we will talk about or deal with is the 3 types of concentrated solutions you can have. So you can have a saturated solution, a unsaturated solution, and a supersaturated solution. And so if something is saturated, it means that it contains the maximum possible amount of solute. That to me is like good sweet tea. You know, it has just the right amount of sugar, just the right amount of flavor, but it's not too sweet. Then you have unsaturated, a solution that contains less than the maximum possible amount of solute. That would be, you know, what we would call weak Kool-Aid, you know, or weak tea or not so good tea. And then supersaturated is a solution that contains more than the maximum possible amount. This is when you call sugary or diabetic in a cup is what I call it. When the tea is so sweet that you see the sugar crystals still floating at the bottom, that would be supersaturated. So a question on your test would be like, all of these are concentrated types of concentrated solutions except. And then you would just remember you had this list and look to see which one was not on it. And so as I pointed out before, I do like questions that say accept this or accept that. So just remember when you see those, that means I'm talking about all but one thing on this list is true, which is that one thing not true. Okay? So moving on. So now that we talked about water and its solubility properties and how we can make concentrated solutions, let's talk about the fact that water has a boiling point. So water natural boiling point is 100 degrees Celsius, 212 degrees Fahrenheit, right? And so when we say that it has a normal boiling point, we mean that it can reach those temperatures anywhere at your house. Well, when you add in solute particles, like for instance adding in salt, this actually increases the boiling point. So why is that? Why when you add in something you can now increase the boiling point? And what do I mean by increasing the boiling point? Meaning that now where it would normally take 100 degrees to make the water boil, it now takes 110 degrees. Well, I'll tell you what happens here is that you see you have all these new little solutes that's in here. Well, it takes more energy to move these solutes than it did just to move all of these water molecules. So on this side, you have the water and you can move it easily, right? Because they're all the same. So at 100, they'll all be moving. 100 degrees Celsius, they'll all move. But once you get over here and you start seeing these solutes, it's not so cut and dry. It's like being in a house that's burning. Is it easier to get 10 people out the house or 100 people? Right. Requires energy. So you can get enough energy to get 10, but 100, maybe not so much. So with that being said, you see the yellow solutes over here because it takes more energy to move them and the water. It increases the boiling point. So now we go from being normal at 100 degrees Celsius to now being more like 110 degrees. So this just says the additional solute affects the boiling point because it affects the vapor pressure. The boiling point is raised with the addition of a solute in comparison to the pure solvent. All the things I just said. The boiling point is raised with the addition of a solute. All right. Freezing point is the same thing. The freezing point is lowered with the addition of a solute in comparison to water by itself. So this is why when it turns wintertime, you know, you're advised to sprinkle salt in front of your doorways so that it doesn't ice over. And that's because the salt crystals will then keep the water molecules from forming those hydrogen bonds that we talked about. Remember, one hydrogen on one water molecule will bond to the oxygen on another. Well, if you have salt between those two, that can't happen. And so when that can't happen, then it takes a longer time for the ice to actually form. And so this is why things like antifreeze are used in your car, is to keep the water from freezing. And so instead of freezing being 0 degrees Celsius, it now becomes like -4 degrees Celsius. And that's because you place a solute in that now is disrupting the chemical structure of the ice, and therefore it takes a longer time for that formation to happen. All right, so now that we've talked about water and its properties, I want to talk about acid and bases, because without knowing it, acids and bases actually end up giving us water. So look at the terminology. Most of the time when you think of an acid, you'll probably think of something like lemon or Coke or some type of battery, because we know normally that those things are acidic. Well, the question is, what makes them acidic? Well, an acid is an aqueous solution or a liquid solution that produces hydrogen ions. And this becomes very important to know, production of hydrogen ions, because we're like, hydrogen ions, what? Hadn't heard of those. Those are just H plus. Remember periodic table? So this is what we consider to be a hydrogen ion. A base is an aqueous solution or a liquid solution that produces more hydroxide ions, or an OH negative, right? And so acids have more hydrogen ions, bases have more hydroxide ions. So an acid, again, is any substance that can donate hydrogen ions. A base is any substance that can help, that can accept a hydrogen ion from another substance. So what happens with a base is that when it accepts an hydrogen ion, you end up having something like, and I really want to see if I could do something like my pen. You end up having something like a hydrogen ion, then you have an OH ion. And what does that give us really? Does anybody see that this is just water? So it gives us H2O. Pretty good for the first time me doing that. All right, so just wanted to show that anytime you have an acid, H plus, right here, and you have a base, OH, when they come together, they make water. And this is why, you take Tums for acid reflux. You have the acid that's in your esophagus, and you take that Tums, it gives us a base. And that base then comes in, mixes with that acid, and neutralizes it by forming water. Now, another trick you could use is just to do baking soda. Just take a teaspoon of baking soda, dissolve it on your tongue, or put it in water, and voila, you created yourself your own Tum, your own base solution that then will neutralize your acid reflux. Now, depending on how bad the reflux is, it may take more than a teaspoon or tablespoon of it. But just know that's the concept behind having those Tums. All right, so let's look at properties of acid. And this becomes one of those questions that all of these are properties of acid except. And so it's like, it's a sour taste, change of color, it turns liquid paper red, it reacts with metals, and it neutralizes forming water, as I said before. Bases, however, are bitter. They have litmus paper turning it blue. They can be slippery and caustic on the skin, and then they also neutralize acid forming water. So for both the properties of acid and bases, all that happens here would be all of these are properties except. So you just have to realize which one is not a property of the acid or base. And last but not least, we want to talk about the pH scale. And hopefully everybody knows the pH scale. So I'm just going to take a look here and try and help you out. So the pH scale is from 0 to 14. Now this is the first thing that we have to remember. pH is from 0 to 14. All right. So you want to remember that. You then always want to remember that 7 is in the middle and it's neutral. All right. So anything from 0 to 7 is considered an acid. See right here, it says acidic. Anything from above 7 to 14 is considered basic. And as we see, it says it right there, basic. All right. So your acids are from 0 up to 7. 7 is neutral, and your bases are 8 to 14. All right. So that's pretty simple, pretty straightforward. Now the thing to know is that on the acid side, that as you go down, you become more acidic. So we now see this more here becomes important. More acidic. That means that 2 is more acidic than 5. So a pH of 2 has more hydrogen ions than a pH of 5 because pH of 2 is more acidic. The more acidic you are, the more hydrogen ions you're carrying in your purse. You're just like, oh, I got all these hydrogen ions, you know. You would think the lower number would have less, but it doesn't. It has more. All right. And that's on the acid side. Now, on the base side, it's opposite. So we start at 8 and work our way up to 14. Well, 14 is the most basic, meaning it has the most hydroxide ions, more basic. So as you go up to the larger numbers on the basic side, you have more. You're more basic, or you have more hydrogen ions. All right. So on this side, a pH of 9 would not be as basic as a pH of 12. So a pH of 12 is most basic. pH of 9 is less basic. This means the pH of 12 has more hydroxide ions than the pH of 9. If we look, though, between the pH 9 and 12, 12 have more hydroxide ions, but 9 has more hydrogen ions because it is closer toward the acidic side. Same here where we see 2 and 5, I'm sorry. 2 is more acidic, meaning it has more hydrogen ions, and 5 is less acidic, meaning it has more hydroxide ions. So just keep that in mind when you're going through the pH chart, knowing that pH goes from 0 to 14. 7 is always neutral. That on 0 to 7 is acidic, and it gets more acidic as you get lower in number on the acid side. And on the base side, it goes from 8 to 14, and you become more basic with your larger number. And so although the sides are opposites, it still tells us a whole lot. All right, and that will end that lecture. If you have any questions, please contact me, and we could try and make sure that we talk about anything that you didn't get. All right, and that will be it. So I'll go ahead and disengage us from this, and hopefully you can hear it.